Some 500 years ago, there was one scientific phenomenon that was, without controversy, extremely well understood: the motion of the celestial objects in the sky. The sun rose in the east and set in the west with a regular 24-hour period. Its path in the sky rose higher and the days grew longer until the summer solstice, while its path was the lowest and shortest on the winter solstice. The stars exhibited that same 24-hour period, as though the heavenly canopy rotated throughout the night. The moon migrated night to night relative to the other objects by about 12 degrees as it changed its phases, while the planets wandered according to the geocentric rules of Ptolemy and later refinements put forth by others. For over 1,000 years, this Earth-centered view of our universe went largely unchallenged and became nearly universally accepted. We often ask ourselves, how was this possible? How did this geocentric picture of the universe hold up without any of science's greatest minds contesting it, for generation after generation for more than a millennium? There's this common narrative that due to dogmatism, like the unchallengeable facts of Earth being stationary and the center of the universe, no one was even allowed to question these so-called facts. But the truth is far more complex. The reason the geocentric model held sway for so long wasn't because of the oft-described problem of groupthink, but rather because the evidence supporting a geocentric universe fit it so well, far better than any of the alternatives that had been put forth. The biggest enemy of progress isn't groupthink at all, but the unrivaled successes of the leading, already established theory. Today, although many complain about groupthink as a major problem in science, it's actually the successes of our current picture of the universe that present the greatest difficulties when searching for a scientific revolution. Although we normally consider Copernicus and his 16th century treatise the beginnings of heliocentrism, that's not exactly true. It might not be a particularly well-known fact, but the idea of a heliocentric universe goes back, at least, over 2,000 years. All the way back in the 3rd century BCE, the legendary scientist Archimedes published a book called The Sand Reckoner, where he begins contemplating the universe beyond Earth. Although he isn't quite convinced by an argument against geocentrism, he recounts the now lost work of his contemporary Aristarchus of Samos, who put forth the following idea. His hypotheses are that the fixed stars and the sun remain unmoved, that the Earth revolves about the sun on the circumference of a circle, the sun lying in the middle of the orbit, and that the sphere of the fixed stars, situated about the same center as the sun, is so great that the circle in which he supposes the Earth to revolve bears such a proportion to the distance of the fixed stars as the center of the sphere bears to its surface. In other words, way back when the Great Wall of China was being built, Aristarchus proposed that the sun and the stars were stationary, that the Earth revolves around the sun, and that the stars are so distant that the Earth's distance versus the sun's size is about the same ratio as the distance to the stars versus the size of Earth's orbit. The work of Aristarchus was recognized as having great importance for two major reasons that surprisingly have nothing to do with the idea of heliocentrism. Why do the heavens appear to rotate? This was an enormous question of the time. When you look at the sun, it appears to move through the sky in an arc each day, where the arc that's observable from Earth is merely a fraction of a 360-degree circle, corresponding to an apparent motion for the sun of about 15 degrees each hour. The stars also move in precisely the same fashion, where the entire night sky seems to rotate about the Earth's north or south pole, depending on your hemisphere, at that exact same rate, about 15 degrees per hour. The planets and moon do nearly the same thing, just with the tiny extra addition of their nightly motion, 12 degrees per night for the moon. The issue is that based on these observations alone, there are two conceptual ways that are equally good at accounting for these observed motions. The Earth is stationary, and the heavens and everything in them rotate about the Earth with a rotational period of 360 degrees every 24 hours. If all we saw were the objects in the sky, either one of these explanations could fit the data perfectly well. And yet practically everyone in the ancient, classical, and medieval world went with the first explanation and not the second. Why? Was this a case of dogmatic groupthink? Hardly. There were two major objections that were raised even back in the ancient world to the second scenario, the scenario of a rotating Earth. Neither one of these objections was successfully addressed until much more modern times during the Renaissance. The first objection is that if you dropped a ball on a rotating Earth, it shouldn't fall straight down from the perspective of someone standing on the Earth. Instead, the ball should fall straight down while the person on the Earth moved along with the rotating Earth. Motion that should appear different from the straight line motion of the falling ball. This was an objection that persisted through the time of Galileo and was only resolved with an understanding of relative motion and the independent evolution of horizontal and vertical components for projectile motion. Today, these properties form the basis of what's known as Galilean relativity. The second objection was even more severe, though. If the Earth rotated about its axis every 24 hours, then your position in space would differ by the diameter of Earth, about 12,700 kilometers, from the start of the night to the end of the night. That difference in position should result in what we know astronomically as parallax, the shifting of closer objects relative to the more distant ones. If the stars were actual objects in space at great distances from Earth, then the closest ones should appear to exhibit this parallax relative to the more distant ones. After sunset, the closest stars should appear to shift by a small but noticeable amounts relative to their positions just before sunrise. And yet, no matter how acute your vision was, nobody had ever observed a parallax for a single one of the thousands of stars visible in the sky. If they were at different distances and the Earth was rotating, we'd expect to see the closest ones shift position from the beginning of the night to the end of the night. Despite this prediction, no parallax was ever observed for more than 1,000 years, until the 1830, in fact, well after the invention of the telescope. With no evidence for a rotating Earth right here on Earth's surface and no evidence for parallax, and hence a rotating Earth among the stars in the heavens, it became difficult to ascribe the apparent motions of the sun, stars, and other heavenly objects by hypothesizing a rotating Earth. The data didn't support that hypothesis, while the alternative explanation of a stationary Earth and a rotating sky, or a celestial sphere beyond Earth's sky, wasn't contradicted by any observables. For that reason, the rotating celestial sphere option emerged as the favored explanation. Were we wrong? In hindsight, we absolutely were. The Earth does rotate, but we didn't have the tools, knowledge, or the precision available to us in order to make quantitative predictions for what we'd expect to see. It turns out that the Earth does rotate, but the key experiment that allowed us to observe it on Earth, the Foucault pendulum, wasn't developed until the 19th century. Similarly, the first parallax wasn't seen until the 19th century either, owing to the fact that the distance to the stars is enormous, and it takes the Earth migrating by millions of kilometers over weeks and months, not thousands of kilometers over a few hours, for the best telescopes of the time to detect it. The problem was that we didn't have the evidence at hand to tell these two predictions apart, and that we incorrectly conflated absence of evidence with evidence of absence. We couldn't detect a parallax among the stars, which we expected for a rotating Earth, so we concluded that the Earth wasn't rotating. We couldn't detect an aberration in the motion of falling objects, so we concluded that the Earth wasn't rotating. We must always keep in mind in science that the effect we're looking for, that we haven't seen yet, might actually be present, including at precisions that are just below the threshold of where we're capable of measuring. Still, Aristarchus was able to make important advances that did survive throughout the ages and that were quite significant for his time. First off, he demonstrated that he wasn't dogmatic about his own ideas, as he was able to set his heliocentric ideas aside, instead using light and geometry within a geocentric framework to concoct the first method for measuring the distances to the sun and the moon, and hence to also estimate their sizes. Although his values were way off, mostly due to observing a dubious effect now known to be beyond the limits of human vision. His methods were sound, and modern data can accurately leverage Aristarchus's methods to calculate the distances to the sun and the moon, as well as the physical sizes of each one. It wasn't until the 16th century that there was revived interest in Aristarchus's heliocentric ideas, as that's when Nicholas Copernicus came onto the scene. Copernicus noted that the most puzzling aspect of planetary motion, the periodic retrograde motion of the planets, could be equally well explained from two perspectives. Planets could orbit according to the geocentric model, where planets moved in a small circle that orbited along a large circle around the Earth, causing them to physically move backwards at occasional points in their orbit. Or planets could orbit according to the heliocentric model, where every planet orbited the Sun in a circle, and when an inner, faster-moving planet overtook an outer, slower-moving one, the observed planet appeared to change direction temporarily. Why do the planets appear to make retrograde paths? This then became the key question for astronomers and those who studied Earth's place in the universe. Now, humanity had two potential explanations with vastly different perspectives, yet both were capable of producing the phenomenon that was observed. On the one hand, we had the old prevailing geocentric model which accurately and precisely explained what we saw. On the other hand, we had the new upstart, or resurrected depending on your perspective, heliocentric model, which could also explain what we saw. At least they could both qualitatively explain what was observed. But in science, it's the best quantitative explanation, the one that accounts for how much of an effect we see, that will win out. Unfortunately, the geocentric predictions in the 16th century were more accurate, with fewer and smaller observational discrepancies than the heliocentric model's predictions. Copernicus could not sufficiently reproduce the motions of the planets with a heliocentric system, even as well as the geocentric model could, no matter which parameters he assigned to the various circular orbits of the planets. In fact, to remedy this, Copernicus even attempted to add in epicycles to the heliocentric model, seeking to improve the orbital fits. Even with this ad hoc fix, his heliocentric model, although it generated a renewed interest in the problem, did not perform as well as the geocentric model in practice. It wouldn't be until the 17th century that the heliocentric model finally gained support and overthrew the geocentric model in a legendary scientific revolution. But why did it take so long? The reason it took close to 2,000 years isn't because of groupthink or a lack of imagination, but rather it took so long was because of how successful the geocentric model was at describing what we observed and how poorly the alternatives fared in comparison. The positions of the heavenly bodies could be modeled exquisitely using the geocentric model in a way that the heliocentric model could not reproduce. It was only with the 17th century work of Johannes Kepler, who tossed out the Copernican assumption that he himself once adhered to, that planetary orbits must be reliant on circles, that led to the heliocentric model finally overtaking the geocentric one. What was most remarkable about Kepler's achievement wasn't that he used ellipses instead of circles, that he overcame the dogma or groupthink of his day, or that he actually put forth laws of planetary motion rather than merely a model of it. Instead, Kepler's heliocentrism, with elliptical orbits, was so remarkable because, for the first time, an idea had come along that described the universe, including the motion of the planets, better and more comprehensively than the previous geocentric model could. There are always three hallmarks of any scientific revolution where a new theory comes along looking to supplant and replace the old one. The new theory succeeds wherever the old theory did dot. The new theory explains an observed phenomenon that the old theory couldn't account for. And the new theory, in comparison to the old theory, makes differing predictions that we can then go out and test. In particular, the highly eccentric orbit of Mars, which was previously the biggest point of trouble for Ptolemy's model, was an unequivocal success for Kepler's ellipses. Under even the most stringent of conditions, where the geocentric model had its greatest departures from what was predicted, the heliocentric model had its greatest successes. That's often the test case. Look where the prevailing theory has the greatest difficulty and try to find a new theory that not only succeeds where the prior one fails, but succeeds in every instance where the prior one also succeeds. Kepler's laws paved the way for Newton's law of universal gravitation and his rules apply equally well to the Earth-Moon system, to Jupiter's and Saturn's moons within the solar system, and to the motions of planets of exoplanetary systems here in the 21st century. One can complain about the fact that it took some 1800 years from Aristarchus until heliocentrism finally superseded our earlier geocentric notions. But the truth is that until Kepler and the advent of elliptical orbits, there was no heliocentric model that matched the data and observations as well as Ptolemy's model did. In fact, it's easy to envision a slightly different version of human history, where the geocentric model would hold sway for even longer periods of time. The only reason this scientific revolution occurred when it did is because there were already well-established cracks in the theory. Places such as for the orbit of Mars, and to a lesser extent Mercury, where observations and predictions failed to perfectly align. Whenever there's a mismatch between what's predicted and what's measured, that's where the opportunity for a new revolution may arise, but even that is not guaranteed. It leads to some fascinating questions that puzzle scientists even today. Are dark matter and dark energy real, or is this an opportunity for a revolution? Do the different measurements for the expansion rate of the universe signal a problem with our techniques? Or are they an early indication of potential new physics? What do non-zero neutrino masses indicate? A simple mixing, as in the case of quarks, or the first step towards a leap beyond the standard model? And what of the Muon G2 experiment? Is this a case where experiment differs from theory, or a case where we've simply made theoretical mistakes in our calculations? It's important to explore all possibilities, even the most wild ones, but to always ground ourselves in the reality of observations and measurements we can make. If we ever want to go beyond our current understanding, any alternative theory has to not only reproduce all of our present-day successes, but to succeed where our current theories cannot. That's why scientists are often so resistant to new ideas. Not because of groupthink, dogma, or inertia, but because most new ideas never clear even the first of those epic hurdles, and are inconsistent with the established data we already possess. Whenever the data clearly indicates that one theoretical alternative is superior to all the others, however, a scientific revolution is inevitably sure to follow. Thank you so much for joining us today. See you soon in another video. Until then, stay curious and remember to dream big.